Object-oriented programming is extremely popular because of the way that it is able to help keep code readable and organized. And when SystemVerilog was introduced in 2005, it caught on to this popular coding paradigm by introducing structs, classes, and interfaces. And although classes and interfaces are generally only used for design verification, structs can actually be used to incorporate object-oriented programming into your hardware design. So in this video, I wanted to show you how to use structs and also some common problems and intricacies that they bring to SystemVerilog. So first, I have this GitHub repo already set up with a bunch of different examples of how to use structures in SystemVerilog. And I have it cloned right here, you can see. And before we get into any of these examples, let's first just create a separate basic example. And let's create testbench.sv. And first, let's just create a hello world. Great, so now let's run this, and we can run it with Verilator. And let's use -- binary to create an executable for us to run. And then now we can run our executable with object dir vtb. And if we run it, then now we see hello world. So now let's create a struct. So a struct can be created by typing in struct, and assuming you have the Visual Studio Code plugin for SystemVerilog, then you should just be able to hit enter, and it should autocomplete to a full boilerplate for a struct definition. So here, let us give our struct type a name. So let's just call it struct type. And also very important, since we have type def right here, we must add _t. to denote that this is a type that we are declaring. And this is just common coding practice that you should follow in any C-style language, is you should always add this _t to denote that this is a type that you are declaring and not a signal or object or anything. Great, so let's add some members to our struct now. And let's add member1 and member2. And let's actually make member2 2 bits just for fun. Cool. So now we have our struct type. So let's create a struct object. Let's call it S, and let's assign something to it and then print it out. And there we go. Now we are assigning 1 to member1, and we are assigning 2 to M2, and then we are printing out both values. And if we run it again with Verilator, you can see that now it prints 1, 2. Let me now add one additional print statement. So here I am printing the struct as just a binary value. And we can see 1, 1, 0. And this is because of this keyword packed. Because what packed means is anytime we create a struct object, we are actually just creating an array where the struct members are all just packed together one after another. So we can see it says 1, 1, 0. That's because M1 is 1, and then M2 is 1, 0. And this will become obvious if I now change these to now print the binary values instead of the decimal values. So now you can see that all that pack does is it just takes each of these members and it concatenates them one after another as if it were just an array. Cool. And before I move on, I want to show you just 2 more ways that you can assign to struct objects. So one way that I've shown is you can grab the members individually. But if you want, you can actually create a struct literal, and then you can list each of the members and then the value you want to be given to them. So I will create M1 equals 0, and then M2 equals 3. And now if I run this, now you can see that M1 is 0 and M2 is 3. And one more thing that I wanted to show you, you can actually assign to an implicit member called default. And with default, let me just set default equal to 0. That means that any members in our struct you choose to not assign, so for example, I could leave off M2, then now that member will default to the value 0. So if I run this, you can now see that even though I'm only setting M1 equals 0, we can see that all of it will now become 0 there. And similarly, if I said default equals 2, maybe let's add one additional member here. Then now the first member is 0, and then the next two members are 2. So this is how to use default in struct literals. And the final thing that I wanted to show you is that if you wanted, you could also create a parameter with a type of your struct. So here I can make a parameter called struct value, and we can use what we've learned from declaring struct literals to give it any value we'd like. So we can say M1 equals 1, and then M2 equals 3, and then just set everything else to be a value of 2. And now we can take the struct value and assign it to S. And now if we run it, we can see that the first value is 1, and then the next value is 3, and then the next value is 2. Cool. So that is the majority of the syntax for structs. Next, I wanted to go into some more intricacies within each of the examples that I have provided ahead of time. The first example I wanted to talk about from the pre-prepared GitHub repository is the float example. And that's because floats are one of the best ways that you can use structs. Because if we look at the IEEE 754 standard for floating point, we can see that each floating point variable is expected to be stored with a sign bit, and then some width biased exponent field, and then some width significand field. So here I have a struct that exactly implements the 754 structure. So first I have the sign bit, then I have a biased exponent width biased exponent field, and then I have a mantissa width mantissa. And apart from just the struct definition, in this package, I also have a bunch of functions, and each one of them will take in a float t type. And this is a great way to demonstrate that floats work very well with functions. They can both act as inputs to functions, and they can also act as outputs to functions. And then here I'm using a struct type as a local param. Great, so this is the package, but now let's actually look at the hardware module that utilizes this package. So here I have float.sv, and it's very simple. Here I'm just calling each of the functions, and then here I'm describing a flip-flop that will just store a single float type. And then here I have a basic always com block that just demonstrates how one might assign to a struct type using each of the members. But the most important thing that I wanted to show you is what the simulation looks like. To run this example, first we have to go into the directory, and then we can run make sim. And now we can open up GTK Wave to view the waveforms. So this is GTK Wave, and so if we open this up and then open the test bench and then open the float module, you can see here the 3 different structs that are declared inside the module. And we can tell that they're structs because each of their members are visible down here. And this is a feature that you can enable on Verilator if you add the --trace structs command line argument. So you can see that if you enable trace structs, then that allows for each of these structs to be dumped into the waveform as human readable format versus just a single array. Great. So now that we've looked at the simulation, now I want to take a look at what synthesis looks like. So if you go into the make file, we can see that we first run SV to V, then we run Yosis in order to properly synthesize our design. And then we can use netlist svg to print out the netlist that Yosis generated as a nice schematic. So if we now make and then the name of this svg, then now it generates this svg file. Now we can see the schematic that's generated. And the most important thing to note here is this section right here, because this is what a struct actually synthesizes to. all a struct becomes after synthesis is just an array where each member of the struct is just bit sliced. So we can say that bit 31 is the sign bit, and bits 23 to 30, this is the biased exponent, and then bits 0 to 22 is the significand, or the mantissa. So overall, structs are very simple to synthesize. One issue with them, though, is if you want to now take this Verilog file that was generated by Yosis and we wanted to simulate it, unfortunately, there's an issue because now this data queue variable is now just a single array. It's no longer a float type. So if we wanted to dump it into a waveform viewer, we will need to reconvert this back into a struct within our test bench. So if we open up our test bench, we can see here that I call in float.dataQ and I assign it to this float type. So now, even if I decide to run gate level simulation, and I already have it set up by running make GLS, and if I refresh GTK wave, you can see all of these signals disappear because all of the structs inside of our float module have been synthesized away. So now they're all just arrays. However, our test bench still has this data queue struct because we intentionally cast it right here so that it can be dumped and observed in a human readable format. And this is one of the biggest reasons why it's very important to put all of your struct definitions inside of a package. Because if we decided to instead put our struct definition inside of this float module, then when we run gate level simulation, then now we lose access to use that struct type in our test bench. So our test bench would not be able to dump any of these values because there's no such thing as a float type anymore because it has been synthesized away. But fortunately, since we've pulled it into this float package, then now we can actually access it whether or not we've run simulation or not. The next example implements just a basic cache. And you can imagine that a cache implementation should be able to take advantage of structs just as floating point can. But there's a little bit of nuance here that I wanted to talk about. So this is what the layout for a float should look like according to Wikipedia. And this is what the layout of a cache should look like according to UC Santa Barbara's ECE 154A course. And we can see that we have a single bit for valid, and we have some field for tag, then some field for data, and then we have some number of ways for this. So you can imagine that we could have this cache block type where we have a valid bit, a tag field, and a data field to implement this structure. However, this isn't actually the best idea, and in this example, I'm going to talk about why. So maybe start to think about the reason for why we should not implement it this way. And instead, I've chosen to take out this data field and create this completely separate block data type. Well, the reasoning is actually because of this associativity parameter. And no worries at all if you are unfamiliar with what associativity does in the context of caching. But effectively, what it will do to our Verilog design is it will drastically increase the amount of logic required to implement our block info array, but it will not affect the amount of logic required to implement our block data array. A quick side note is I have an info width local parameter, which is determined by the number of bits or the size of this block info struct that we declare. And this is done with the system task bits. Bits will grab the size of whatever you put into here. So this is a great way to parameterize your design based off of the width of one of your structs. So this is just a quick side note. So now if we open our cache implementation, you can see that it's just a basic cache that only supports read hits. So it's very basic, but we can see that we have this for loop down here. In this for loop, we'll check our cache line info, and the amount of times that it runs this for loop depends on the associativity. So as we increase our associativity, you can see that the logic required to implement this for loop will go up. And another side note is Vivado does not actually support block RAM inferences when dealing with either multi-dimensional arrays or when dealing with arrays of structs. So therefore, I've chosen to implement these arrays not as multi-dimensional arrays of structs, but instead just as a normal array with Verilog style syntax. However, we can cast out the values later so that we're still taking advantage of structs. So now let's see what a tool like Vivado will synthesize this design into, assuming that we have an associativity of 1. Great. So this is the netlist that Vivado just generated. And you can see that both the block info and the block data arrays were both synthesized into block RAMs. But now, if I choose to increase the associativity, and let's keep the cache size the same by now decreasing the number of sets, then now we should get a very different picture. And now if we open up what has just been generated, by increasing the associativity, we've now drastically increased the amount of logic required to implement our design. But if we zoom in, then we can see all of this logic is actually just for the block info. And we actually still have all of the block data completely isolated and still very optimized into our block RAMs. And this was only possible because we decided to separate out our block data from our block info. So it was good not to combine them all into one struct so that our synthesis tool can run more optimizations. And now this brings us to our final example, labeled Testbench Example. This example is very basic and it just has a single test bench in it. But this test bench has a struct definition that does not have the keyword packed. And this is because when you create a packed struct, it prevents you from using any unpacked data types, such as strings or dynamic arrays. So this is a perfect example of when you would want to use an unpacked struct, because here I am creating several different tests, each with a test name, a 2-state test length, and then a dynamic array with test contents, and then a 4-state value with the expected maximum. And the next thing I wanted to show you is the struct literals that I demonstrated in the basic example can actually be nested along with dynamic array literals as well. So we can see that here I have a dynamic array tests, which I'm declaring with an array literal. And then here I have a struct literal with the test t type. And then inside each of these literals, I then have another array literal. So struct literals and array literals are intercompatible with each other. So thank you so much for watching. You can find this repo in the description of the video where you can run each of the examples yourself. Here's a getting started guide for installing the tools and for running the examples. And here are some additional references and resources if you are looking for further resources on using structs in your Verilog design. So thank you very much, and I look forward to seeing you in the next video.